In this video, I'd like to talk a little bit more about how we determine electric fields from electric potential. So the idea that we introduced in the last video is that the electric field essentially is the slope of the electric potential. But this is a little bit tricky because electric potential is just sort of a value in space. Each spot in space has some value for the amount of potential there, whereas electric field is a vector. And so we were talking about how do we then get a vector from this scalar, from just this value, the potential. And what we wrote down last time is that if we think about some hill where these are contours of different values for amount of potential, so maybe we're at 5 volts here, and maybe this contour here is just 1 volt. What we realized is that we can take what we call partial derivatives, right? So if we want the slope, and we want the slope in a specific direction, we can define some axes, say an x-axis and a y-axis, and we can think about the slope in each specific direction. So if I want to get the slope in the x direction, I say that the electric field in the x direction is the opposite of the derivative, the partial derivative of v with respect to x. That says just do the derivative in the x direction. And if I want the y direction, then I take the slope in the y direction. And if I have some z direction, I could also do this in the z direction. So this is convenient. This gives us the different components of the electric field vector by taking these different derivatives. Now, notation-wise, this is a little bit clunky, right? Because if we want to write the whole electric field, then we need to write all of these together. And so we would say minus dv dx in the I hat direction, plus minus dv dy in the j direction, plus minus dv dz in the k direction, right? And the electric field is this whole thing. And so what would be nice is if we had a more compact notation for this, and conveniently mathematicians are very good at coming up with compact notations for us. And so what they do is they come up with what's called an operator notation, where we taking the derivative part in the I hat part, and we sort of, if you will, factor a v out of each of these terms, right? The thing that's common in all of these terms is the v, so we kind of pull that out of all of these terms, and then we can write this like follows. We can say E is minus d dx, d dy, d dz, all operated on v. So this says the exact same thing, saying we're going to take the derivative in the x, the derivative with respect to y, and the derivative with respect to z, and make this be in the I hat, the j hat, and the k hat direction. And this whole complicated dealio here, we give that a special notation. The notation for that is something called del or grad. All right, grad or del, and it's an upside down triangle. An upside down triangle means that we want to do this. We want to take the partial derivative in each direction. I should be clear, the minus sign is not part of del, so usually this minus sign gets factored out of the whole thing. So we can write this equation now in shorthand. We can just say that E is del or grad v, and this operation minus del v, where del is a vector, right? Because it has an I hat, j hat, and k hat part. V is not a vector, and so this operation gives us a vector. So we can do an example of this. So let me do an example here. for everyone. So if we want to do an example, let's consider the case where we have some potential V, and we'll take that V to be the following. We'll call it A x cubed y minus B xy squared plus cy. All right, let's take that to be our potential function. And now the question is evaluate. Right, we want to evaluate E. E is grad V. All right, so we want to do this operation. And so remember, grad says take the derivative, the partial derivative in each direction, and call it the I hat, j hat, k hat part. So what we do is we say, all right, E is this grad operator operated on this function. So first, in the I hat direction, right, in just the I hat direction, I need to take the derivative with respect to x. So that makes this 3ay x squared. That's the derivative with respect to x here. Derivative with respect to x here is minus by squared. And derivative with respect to x of cy, well, there's no x's there, so that's just a constant, so that's 0. So now I have an I hat part. And then, I should be very careful. Right, I almost forgot my minus sign in this equation. Very important to keep that minus sign around. Right, so E is minus that. All right, and then plus, and we're going to do minus. Now we take the derivative with respect to y. So the derivative with respect to y here is ax cubed, right, because that's the constant in front of y, minus 2bxy, right, that's the derivative of this term here, and then plus c, that is the derivative here with respect to y, j hat. And so there you have it. That would be the answer. The full electric field would have some I component and some j component. If I gave you specific values for x, y, a, b, and c, you could solve this numerically. So that is the idea of taking the gradient of a scalar function. Is you use this grad or del operator, you apply it to a scalar, and the result is you get a vector.